Hi everyone, our lesson today is combination without ordered sampling and without replacement. So we have here 5 objects and we are going to withdraw these objects in 3 consecutive turns, and we are not going to return any object to the urn after each withdrawal, and we are going to withdraw in order. Actually, this is a problem we have studied before. It is permutation without replacement, but why we are repeating it here, we are going to see. So in the beginning, we may withdraw any one of these 5 objects, and that is the first draw. And for the second draw, there is only 4 objects available out of the 5 because we are not returning the object to the urn. And in the third withdrawal, we have only 3 objects remaining because 2 objects has already been withdrawn, and this is the third draw. And now we have all these possible outcomes. As we have seen before, this is permutation for n objects taken r at a time, which is p53, and it is equal to 5 times 4 times 3, and this is equal to 60, which is the number of possibility of permutation without replacement. So now we are going to move from the case of ordered sequences to the case of not ordered sequences. In what sense? We have all these ordered sequences. We take, let's say, sequence 1, 2, 3, and out of this sequence we have 6 sequences in different orders. We are going to count them as one sequence. So we're going to cancel these 5 here. And for the sequence 1 to 4, we have also 6 different orders, so we cancel these 5 here. And from the sequence 1 to 5, we have also 6, so we cancel the extra 5, and we keep doing so. And we can see that these sequences in the tree are dwindling until we arrive at the final sequences here, which are the sequences without order. So these 10 sequences have been derived under these conditions: 3 consecutive turns of withdrawal, and now we have 3 symbols in it, and no replacement of any object, and no order. So if we have 1 to 3 or 3 to 1, they are going to be counted only once. Now let's see the number of sequences that have been generated. These are the numbers, and we add them together and we get 10. So what is this 10? We call it the combination of 5 objects taken 3 at a time without replacement. Here there is no replacement. We haven't written R to refer to replacement, so every time we found the letter C with no any annotation symbol on the top, so this is combination without replacement. Now we have to remember important fact that this tree is originally was derived from the permutation of element without replacement, and it gave us combination of element without replacement after we omitted all ordered sequences. So what is this 10 here? It is 60 divided by 6. It's the number of permutation without replacement divided by the number of repetitive sequences. So the 60 here represent permutation of 5 objects taken 3 at a time, and therefore we can write that permutation 5 is 3 divided by 6 is equal to combination of 5 is 3. And this combination is without replacement, and this permutation is also without replacement. Now what does this T means? It means the number of ordered sequences. How can we derive that? We use the tree. For 3 objects we have 3 numbers, and we are withdrawing this number without replacement, so we get 6 ordered numbers, and so this is what the 6 here means. So now we have permutation of 3 numbers taken 3 at a time, and that is 3 times 2 times 1, or permutation of 3 objects or 3 numbers taken 3 at a time, and this permutation is equal to 3 factorial. So we can write this equation as follows. We can write it as permutation 5 3 divided by permutation 3 3 equal to combination 5 3, and we can replace this permutation 3 3 by 3 factorial, and now we can replace the 5 with n and 3 with r to get the final formula, which is combination without replacement is equal to permutation without replacement divided by r factorial. So we write the final formula CNR, which means combination without replacement of n different non-ordered objects taken r at a time. So what is n? It's number of the object in the set. This is the objects we are going to combine. And what is r? It is the length of the generated sequences or number of symbols in the sequences. So if we have the sequence contains 3 symbols, so it is r is going to be equal to 3, or size of the sample point, and they all mean the same thing. Now what are the conditions to apply this formula? Conditions are: number 1, objects are defined over the set. So it's defined over a set, not multi-set or not a list, and the object in the sequence are not ordered. There is disregard for order here, and we are withdrawing without replacement. So without replacement means what? Means the letter or the object in the sequence are not going to be repetitive. So now we are going to investigate the range of r. So if r is equal to 1, so we are combining, let's say, 5 objects taken 1 at a time, or we are going to get what? 5. We can use a formula if we want by substituting r equal to 1. So we get pn1 divided by 1 factorial, which is equal to pn1, and pn1 according to the previous formula is n factorial divided by n minus 1 all factorial, or n times 1 only one time. So we can get finally n. If r is equal to n, so we are combining 5 objects 5 at a time, we are going to get, the answer is 1. So we can substitute in the formula if we want. So we have pnn divided by n factorial, and pnn is n factorial, so n factorial divided by n factorial is 1. So if we combine 5 objects 5 times, no matter in what order we put these 5 objects, we are going to get the same object, the same counted object, which is 1. So now we write r is ranging from 1 to n, and in this case the maximum size of a generated sequence is n, and the minimum size of a generated sequence is only 1. And we have to remember that no replacement means that objects do not repeat in any generated sequence. So if we have objects A, B, C, D, and E, so we may generate sequence such as B, A, C, E, D, but we are not going to generate sequence such as B, A, C, E. A cannot be repeated, C cannot be repeated, and so on. We can also create an algorithm to combine these objects together. So we start with 1, and we combine 1 with 2, 3, 4, 5, and then with 2 we combine 2 with the remaining 3, 4, 5, and we combine 3 with the remaining 4, 5. Now we stopped here because the length of the generated sequence is 3. If we continue, we are going to get a sequence of size 2, which is not required here. So let's see how we can do that. We have these 3 sequences. Now we are going to combine them one after the other. So we start with the sequence 1, 2, 3, 4, 5. We combine 1 with the rest of the sequence. So we can have 1, 2, and 3, and 1, 2, and 4, and 1, 2, and 5. and now we combine 1 with 3, 4, 5, so we have 1, 3, and 4, 1, 3, and 5, and that's over. And now we combine 1 with 4 and 5, so we have 1 with 4 and 5, and now we generated 6 sequences. So now we go to combine 2 with 3, 4, 5. So we start with combining 2 with 3, 4, 5 here. So 2, 3, and 4, 2, 3, and 5, and then we combine 2 with 4, 5, so 2, 4, 5, and that's the end of it. We have now 3 numbers. We have now 3 objects in the sequence, and now we generated 3 objects. Now we go to the last one, which is 3, 4, 5. It's already generated sequence with a length of 3. So we have 1 element only. And if we add all these together, we are going to get combination of 5 objects taken 3 at a time equal to 10. This is like an algorithm to generate a combination of 5 objects. So now we have a combination of 5 objects taken 3 at a time, and the number of generated sequences is 10. And every sequence can be arranged in 6 ways. So let's use the tree diagram. We have 3 objects in each sequence, and these are non-ordered. Now we are going to order them to create all different orders without replacement. So we get 6 ordered sequences here, and these 6 ordered sequences are 3 times 2 times 1 equal to 6. So 3 times 2 times 1 equal to 6, or it is 3 factorial equal to 6. So what do we do now? If we have here 10 non-ordered sequences, how do we turn them into all ordered sequences? We multiply the 10 by 3 factorial. So in this side here now, we have the number of all ordered sequences, which is permutation without replacement. And this is 10 times 6, which is 60. And this 60 is permutation without replacement of 5 objects taken 3 at a time. And now we can see the relation between combination without replacement and permutation without replacement. We just substitute 5 by n and 3 by r, and we get this formula. So permutation of n objects taken r at a time is equal to the combination of n objects taken r at a time times 3 factorial, and all these without replacement. So we arrive at this final formula here, but in a reverse way. If we have 5 different objects defined over a set, of course, we can use this tree diagram to create all kind of combination as we have seen before. So for 1 we combine it with 2, 3, 4, and 2 we combine it with 3, 4, 5, and so on. And for object 2 we combine it with 3, 4 only, and for object 3 we combine it with 4, and we continue until we get all these objects according to the previous algorithm. Thank you for listening and have a good day.